Okay, today we are seeing how sinusoidal functions can be used to model certain specific data charts, collections of data. So example 1 goes into data that's been retrieved from Stats Canada. So using data from Stats Canada, determine if there is a period of time over which changes in the population of Canadians aged 20 to 24 can be modeled using a sinusoidal function. So basically, can the data shown, which is the population over time, be modeled by a sinusoidal function? Okay, and it's talking specifically about, we know the population of Canada is continually increasing, but it's talking specifically about Canadians between the ages of 20 to 24. All we're going to do is plot this thing. So you have a blank grid. You can give it a horizontal and a vertical axes. Time is always the independent, so this is going to be years after, what's the first year that it starts in, our data? Starts in 1976. So this will be years after 1976. Start at 0, and we need to be able to go all the way up to 2005, which is about 30 years after. So we're going from 0 to 30. So go ahead and split up your horizontal axis into a scale that allows you to go from 0 to 30. And then the vertical axis, the lowest population. What do you think the lowest population is there in our chart? They look to be all above 2 million. But in order to give ourselves some space, why don't we go from, we'll go up to 3 million. And we won't leave anything out. We'll do the full chart. So we'll go up to 3 million. And we should label that that is population. And it's measured in millions. I don't know, we'll have to look at our data. It won't go higher than 3 because I don't see any numbers bigger than 3 million. So go ahead and plot all that data. Okay, so you have the year 1976 is 0 on our graph, right? And at that point it's 2.25 million. So you'd go ahead and try your best to find the spot 2.25 and put a dot. And maybe input, maybe don't do every single year, maybe do only the even years. Do 0, 2, 4, 6, 8. And we'll double check up here when you're done. Okay, your graph should look something like this. If it doesn't, then make it look something like this. So there's a minimum right around the 20-year mark, between like 18 and 20 years after 1976, and then it goes back up by the year 2005. It's back up to its max at 2.25-ish.
What? Max reaches 5. 2.5.
Nope, 2.25.
No, in 1984.
Oh, yep, nice. So it does go, oh yeah, sorry. Yeah, 2.5.
Does it reach max?
Nope, you're right. Mistake. Okay, so does the population fluctuation appear to be sinusoidal? Periodic? It does. It repeats itself. Okay? Good enough. That's all we were trying to identify. It does repeat itself, so it can be represented by a periodic function. Okay? Example 2. Make predictions. Example 2, you have a picture of a Ferris wheel. You're told that the relationship between the height above the ground of a person riding the Ferris wheel and time, so height above the ground and time, can be modeled using a sinusoidal function. Describe the effect on this function if the platform from which the person enters the ride is raised by 1 meter. So they're getting on before the minimum point. What do you think this would make? What would happen to the graph in this case? So if they got on at the very bottom car, then they'd be starting at 0, 0, right? And they would be going up and back down and up and back down. Okay? But now they're not getting on at the very bottom car. They're getting on 1 meter up. So they're getting on here and then going down. And then following the exact same time versus distance. What happened to the graph? Which way? Well, the 1 meter was vertical. We don't need to know specifics, but yes, we would say the graph shifted to the right, and we don't know how far. We could calculate it. Whatever the angle difference is between that bottom car and that car that's 1 meter off the ground, whatever that angle is, that's how far it moved to the right. Does that make sense? Okay? Except we're talking about time. So it's really however much time it took to get from here to here. Okay, that's all we needed to discuss was what's the effect if the platform is raised by 1 meter. B says, describe the effect on this function if the Ferris wheel turns twice as fast.
Then it's going to do the exact same thing, only it's going to be
Horizontal compression by a factor of half. Nice. So K would be 2. It would complete 2 period lengths within 360. So every single point along this red curve, let's just pick a couple of our key points, it's going to now be half the distance from the y-axis. Make sense? So now we're going down, up, down, up. Yeah, except twice as fast. Something in here didn't quite go right. This one is not half the distance. That's why. We should be able to go from here down to there, and then back up to whatever half the distance is with that one. Should be back up. It'll be back to here, actually, wouldn't it? Get what I'm saying? Good enough? Good enough. Okay, that's example 2. So, explaining the first part again, the red line. Because the platform is not at the lowest point of the wheel, a phase shift is introduced. The rider does not reach the lowest point until the wheel turns through that phase shift. If the platform used to enter the ride is raised 1 meter, the phase shift increases, and it takes longer for the rider to reach the lowest point, so the graph will shift to the right. If the wheel spins twice as fast, that's what we did in B with the green line, the period will be half as long. The graph will be compressed horizontally by a factor of 1/2. Example 3. Use a sinusoidal model to determine values. So here we have the height h in meters above ground of a rider on a Ferris wheel after t seconds, so its height with respect to time, can be modeled by the sine function h of t, height with respect to time, is equal to 10 times the sine of 3 times t minus 30 plus 12. And we are asked to graph the function. We're going to do it using our extended table of values, and then we'll graph it on the graph paper there, and then we will discuss it. Okay? So go ahead and fill in your standard values for y equals sine of x. So as we turn through 0 degrees, 90 degrees, 180, 270, 360, y is for sine of x. When x is 0, y is 0 because it goes through 0, 0. It reaches its max at 90, goes back to its rest, reaches its min at 270, and goes back to its rest by 360. Now, let's give this we'll change our y values here. We've got stretch compression, reflection, translation. After a stretch compression, what's our vertical stretch? By a factor of 10. Okay, I'll write the equation up here. Height with respect to time is 10 times the sine of 3 t minus 30 plus 12. So stretch of 10, which 10 times 0 is 0, 1 becomes 10, negative 1 becomes negative 10. No vertical reflection, so we look to the vertical translation, which is up 12. 0 becomes 12, 10 becomes 22, 0 becomes 12, negative 10 becomes 2, and 0 becomes 12. Let's look on our other side, our horizontal. What's going to change with x? It's got a k value of 3, which translates into a what? Stretch or compression? Compression by a factor of 1/3. So all of our x values are being divided by 3. 0 stays 0. 90 is now 30. 180 is now 60. 270 is now 90. 360 is now 120. There is no horizontal reflection, but there is a phase shift. Is d, what's the value of d? Positive 30. So we're moving to the right 30, so we're adding 30 to each of our values here. So 0 becomes 30, 30 becomes 60, 60 becomes 90, 90 becomes 120, and 120 becomes 150. Then we can just kind of record our points. So we're going through 30, 12. We're going through 60, 22. We're going through 90, 12. So the rest is 12. The max is 22. The min is 2. Going through 120, 2. We're going through 150 with a y coordinate of 12.
Would there be a reflection if there's a negative on front of 10?
Yep. Yeah, and that's easy to do with this strategy because all that would happen is you would just change all these to a negative number. Yeah? Or in that case, if it was in front of the 10, all our red vertical values their signs would swap. Okay, you have a graph there. It doesn't need to go into the negatives. Not far anyway, because the minimum value is 2. horizontal axis is time, the vertical axis is h of t. And we can plot our points. So probably choosing a scale on the bottom would be good. We're going from, let's graph a couple of cycles. Let's graph 2 cycles. So let's go up to 360. No, let's go up to 300-ish. So split yours however it seems to make the most sense to you. And then we can plot our points. So we've got, we need a height scale as well, from 0 to 30. And now plot our points. 30, 12. Go ahead and do this on your own and then just check the board to see how you're doing. I knew that my y-intercept was going to be 2. It was going to be at the minimum. The way I did that is just I kind of traced the rest points. There's 60 degrees between every rest. So if this one is 60 degrees here, then there'd be 60 degrees here, which would bring me to the next rest at negative 30 on my horizontal axis. And the minimum will fall right in between negative 30 and positive 30, which is 0. So that's how I knew that way. The other way to look at it would be knowing that you have a minimum at 240, a minimum at 120, 240, 120, 0 would put this minimum right in between your other two. So whatever connections you can make. If you are really stuck and you wanted to know where your x-intercept was, or sorry, your y-intercept, you could just throw 0 into this equation and put it in your calculator.
Isn't it the closest minimum, or just the minimum?
In this case, the minimum is right on the axis, but if it had shifted different amount left or right, then that wouldn't, you can't count on that.
Further back.
Okay, now that we have that graph drawn out, we're going to determine each of the following: the max and min height of the rider above the ground. What's the maximum height of the rider above the ground?
22.
22 meters. The minimum height above ground? 2 meters. B, the height of the rider above the ground after 30 seconds. 12 meters. C, the time required for the Ferris wheel to complete 1 revolution.
150.
It's from 0 to 120. The other way to remember that is up here. We've got 360 divided by k. 360 divided by 3 is 120. Another way to do it would be look at your points here and say, okay, from my rest to my max, through my rest to my min, back to my max, or sorry, back to my rest, 150 minus 30 is 120. So 120 seconds. And ladies and gentlemen, that is it. That's all. Yeah? Again, we could have used the notes we took at the beginning of class to get your period length. It's 2 times your max minus your min. The practice problems are at the bottom of that page, page 328, 1 through 11.